Now, after this observation, we are going to turn our focus on the simplest case of infinite sets, which are the countably infinite sets. Now, at this point, we have a new term here, countable. What does countable mean? And we start here with a definition. The set of natural numbers, see this set 0, 1, 2, 3, etc. towards infinity, this set of natural numbers has cardinality aleph null. Now this is our definition, and this we define to be the cardinality of natural numbers. And natural numbers is the benchmark set for countability. Now what does countable mean? If a quantity is finite, it's obviously countable, meaning that you can start and you can start counting the elements of a finite set, list them one by one, and then actually finish it. Okay, but when it comes to an infinite set, we do have countably infinite sets, and what this means is not that you can actually reach the end of the set. It means you can actually list them in a way that I can deduce the element, let's say, enumerated by a certain procedure. Now, with natural numbers, that procedure is also natural because, well, it's 0, 1, 2, 3, and goes on like that. I know which number I'm referring to when I, let's say, okay, the number that is the 200 in this set. Okay, there is a natural ordering of these numbers, and if you list them in this way, whatever number, let's say, you give me, there is a corresponding number. Okay, of course, so you are going to give me that number from the set of natural numbers also. So there is a natural relationship here, which is actually identity. So it's going to be the benchmark, and the set of natural numbers we say to be countably infinite. Let me repeat this. It doesn't mean that you start counting it and you can actually reach the end. It means there is a procedure that you can refer to each element of this set in a distinct way, in a unique way, let's say. Now, that's the definition. And what about the other sets that we can actually refer to? And the definition of a countably infinite set is given here. If there exists a bijection from a set A to the set of natural numbers, then we say that the cardinality of set A is aleph null, and set A is said to be countably infinite set. Okay. Um, the bijection definition is of course crucial here. If you remember, we said that if you can define a bijection between two sets, then in cardinality they are equal. So that is going to be our definition. And when you want to prove that a set is countably infinite, for instance, the first thing you can try is coming up with a bijection between that set and a set of natural numbers. Here's a simple example, actually two examples. The set of even numbers is defined in this way. For any natural number, k, 2 times k is an even number, so set E is defined as the set of evens where um, any element x can be written as 2 times k, where k is a natural number. So it's this set. Now, first of all, observe that this set is the subset of natural numbers. Every element is a natural number, so it's included in the set of natural numbers. But now look at this function. F of x equals 2x from set of natural numbers to the set of even numbers. Now, since I'm defining a bijection, I know that it's invertible, so it's not really significant which set is the domain and which one is the codomain, because the function is going to be a bijection. It can go both ways. You can define its inverse. For instance, you can define the function x over 2 from set of evens to set of natural numbers. Any bijection you can come up, its inverse is already defined as a function. So that's not significant here. So whichever way is easier, you can prefer it. So function f of x equals 2x is a bijection from the set of natural numbers to the set of evens, which means set of evens in cardinality is aleph null. So it's a countably infinite set. Essentially what I'm saying is the set of even numbers has the same number of elements as the set of natural numbers. Again, this is a little bit counterintuitive because it looks like it's half as big, but that is not the case. So that's some um, property of infinity, let's say, which is a little bit difficult to grasp due to the way we think. So this set of evens, it's an infinite set, but it's not smaller than the set of natural numbers. It's in fact in cardinality the same. Another example is the set of integers. Now, in fact, this set is a superset of set of naturals. So it includes set of naturals. So it looks like it's a bigger set, but let's see whether it is bigger or not. Now define this function from set of integers to set of naturals. If the number, the integer, is an even number divided by 2, so 0 maps to 0, 2 maps to 1, 4 maps to 2, 6 maps to 3, etc. Or if it is not, which means it's an even number, it's an odd number, then add 1 and then divide by 2 and negate it. Well, actually, I realized that it should be from set of naturals to set of integers because this produces negative numbers. Therefore, take any natural number. If it's even, divide by 2, then you will get all natural numbers. If it is odd, then add 1. Okay, so 1 is going to be add 1, 2, divide by 2, 1, and negate it. It's going to be minus 1. 3 will be what? Add 1, 4, divide by 2, 2, negate, minus 2. 5 will be add 1, 6, divide by 2, 3, negate, minus 3. So you see, with this procedure, I'm obtaining all of natural numbers from the even natural numbers, and I'm obtaining all the negative integers from odd integers, odd natural numbers. So you see, every number in the codomain set of integers is covered with this mapping, and this is clearly a bijection from set of natural numbers to set of integers, which means set of integers has also cardinality aleph null. So it looks like it's a bigger set than the set of naturals, but it really is not in terms of cardinality. Set of even numbers, set of natural numbers, or set of integers, or usually you can also separate them, set of positive integers, set of negative integers. They all have the same cardinality, and they are all countably infinite sets. Now, of course, finite sets are countable because, as I said, you can actually count and finish them in theory. However big they are, as long as they are finite, they are always countable. And the subsets of any countable set is also a countable set. You cannot take a part of a countable thing and that turns out to be uncountable. That is impossible. The subset of any countable set is going to be always a countable set. Be careful here. The subset of a countably infinite set might be both, might be a countably infinite set, but it can also be a finite set, right? That's also countable, But you see, the statement is not saying any subset of a countably infinite set is countably infinite. That would be wrong because finite sets, some finite sets will be subsets of countably infinite sets which are not going to be infinite.